Hello. It's Hi guys. Hello again. Let's talk about breadth first search and depth first search. So this is BFS and DFS. This stands for breadth first search, and this stands for depth first search. For now, so that we know what we're working with, let me draw a graph at the middle of the screen. So this is our starting point, denoted by S, and we have a path to A, a path to C, and then a path to B, and then from A we have a path to E, from B we have a path to E, from B we have a path to D, and from C we have a path from F to G. Okay. Now, breadth first search, the visualization of breadth first search is you try to start, of course, from U, and then try to take a look at all your first level connections. So that would mean this one, first level connections, and then you try to expand until you finally get what you're searching for. That's the intuition, breadth first search. The intuition of depth first search is from your network, you try to select a path and then traverse to its deepest node there, then select another path, then traverse to its deepest node, that's your iteration 2, and then select another path, traverse to its deepest node, path 3, and then traverse to its deepest node. So if we try to number this just so we have reference, perhaps we can do it this way, 3 and 4. For the BFS, let's number it as well. We begin with U, and then you expand to your first level connections, and then you expand to your second level connections. So one way that could help us understand this a little bit more in terms of coding is that BFS is a queue, DFS is a stack. I'll try to show you what I mean. If you try to begin with S, say for example, you're looking, that's an I, you're looking at S because that's where you are. What would you do in BFS? Well, you try to populate your list with your first level connections. Of course, this data is already encoded into your code. You know that there's a path, there's a dictionary, there's a key value pair from S to A, there's a key value pair from S to C, there's a key value pair from S to B. And so you can conveniently just add the first layer of friends to the search. In order to help us end our search, let's try to pretend that we're looking for we're looking for someone who's selling mango in our network. That's you. These are your Facebook friends. You're looking for someone who's selling mangoes. So let's try to search the social network for someone who's looking at who's willing and available to sell mangoes to us. And let's first try breadth first search. So breadth first search, I am starting at S, I'm looking at S, and then I can push to the queue all of my first level friends. And the way I did that is to follow the rules of a queue where I see a first as a first level friend. Of course, these are all my first level friends, but I do have to insert them in some order because I can't insert them all at the same time. Perhaps I insert A first, B, then C. That's just a convention. And just to give you a visualization on that, it's as if I pushed, it's really as if I just pushed A here, and then after pushing A, then I push B just behind it, and then push C after B, because it's a queue. A queue by nature, you have one entry point and then one exit point. It's a first in first out system. A comes in first, A would have to leave first. So that's our queue. So I'm looking at S and I have all my first level friends. What BFS does is it tries to pop whatever is in front of the line. So now I'm looking at A. I'm looking at my first friend. And what it does is, if I'm looking at my first friend and that is not a mango seller, because I'm looking for a mango seller, what it does is it discards it, but after discarding it, it tries to send in to the back of the queue the other persons that are connected to it. So say for example, let me just copy B and C first because nothing happens to them, but something happens here. A, the one we're looking at, is connected to E. So E in turn gets pushed to the back of my queue. We repeat the process again. Now we're looking at B because B is the next element that's on front of the queue. And we know that B is not the mango seller, so we don't do anything to B. We don't print out anything, but we do note that B is connected to E and B is connected to D. So after popping B, C becomes the new element that is that's in front of the queue. E we already know is already inside the queue, so we don't need to add him, her, they anymore. What we can do though is, because B is connected to D, we can add D to the back of the queue. So at this point, we were already able to look at A and B. Let's keep going. Now I'm looking at C. And because I'm looking at C, I know that E and D just get copied because nothing happens to them yet. C is not a mango seller, so we just continue. But C is connected to F and G. So we can say that F and G, please go to the back of the line. Now we're looking at E because E is the one in front of the queue right now. D gets copied. E is not a mango seller, so we just continue. And we just copy F and G too. Is there anything connected to E? There's no one, so we don't have to add any one or anything or any value at the end of their queue. Now we're looking at D. D, is there something connected to D? No, nothing. So there's nothing to add at the back of the queue. So we just pop it, and then the guy at the front of the line is now F. Now we take a look at F and we notice that, hey, mango seller. And then at this point, we stop. But the iteration, please notice that ED. I first tried to search, sorry, that's an incorrect highlight. I first tried looking at A, B, and C, which are, sorry, I shouldn't have used yellow because yellow is for DFS, but this one, I looked at A, B, C, and then it's the first layer of friends that I have, and then after completing the first layer is the only time that I jumped to the second layer, E, D, and then once I reached F, then I'm going through the ones at the second layer. If F wasn't, if it happened that F wasn't the mango seller, then I would continue to G, thereby searching all the people in my second level friends graph. So that's BFS. It's like you're searching per connection level. It's BFS. Okay, now DFS is the same. If you try to code it, it's the same. You just change the data structure, and this is a very nice way to say that the choice of a data structure really affects how your algorithm behaves, because in DFS we have a stack, right? So let's try to do that. If I'm looking at my starting point, my stack would be, and this is a first in, last out. So what am I trying to say? Let's try to ito, Pringles. This is the Pringles scan. If I try to put something here, the element that I put first is the last that would come out. So for purposes of making the demo a little bit richer, let's try putting, let me erase this and make a more appropriate representation. Suppose that's my stack. Oh yeah, that's my stack, and I put elements here. Say for example, I insert C first. C, B, and then A. I insert it first. And of course, you can insert it in your own way. I just chose that order so that it would make the looping a little bit longer, so that we can observe the intricacies of the algorithm. That's gonna be the way to go. If we pop the stack, we're looking at A. So the next thing we know is we're looking at A, and the stack would look like this, BC. Since A is not a mango seller, we say that whoever is connected to A, please push it to the top of the stack. So the top of the stack now becomes E. Compare it with this one. It's in reverse. It's not really in reverse. It just follows the rules of the stack. So the new added, the element that gets added in is at the top of the stack, not at the back of the line. All right. So if that's so, the next thing that we're gonna be looking at is E, because that's the thing that we pop. You can't really access elements at the middle of the stack or of the queue. You can just pop or push. So when we pop this, we're now looking at E. Is there anything connected to E? We say there's nothing connected to E, so there's nothing to add. I'm left with B and C. If that's the case, next thing I'm looking at is B. Is there anything connected to B? Yes, there is. So please add D to the stack. Now I'm looking at a popped stack. I look at D. Is there anything connected to D? No. So I don't add anything to the stack. I'm left with C. I'm looking at, let me try to just continue it here. So I'm looking at C. If I'm looking at C, what do I get? I push F here, and I push G here, there. So that we exhaust. It's almost as if I plan to exhaust the input. C is not yet the mango seller, so we continue. We take a look at the element on top of the stack, so that's G, which is not a mango seller, so we continue. We're now looking at F, which is a mango seller, and that's the time that we stop the search. Now notice here in our depth first search that the first thing we try to do is go deep. Say for example, here is my first layer, but here's the first among the elements in my first layer that I saw. Let's go deep into that rabbit hole and let's see what we find. AE. After E, there's no more. So if there's no more, let's proceed to B. You're the next friend in my first level. And then let's go deep. That's B and D. So it went deep. And then after processing B, then that's the time that we go to C, and then C would process F and G. So there. So depth first search, Q. Breadth first search, Q. Depth first search, stack. The change in the data structure that you choose can have an effect on the behavior of your algorithm. These two algorithms are used to find the closest. Let me check my notes. Both of these algorithms try to find the closest possible answer to a solution embedded in a network, which can be useful in a lot of things. Actually, this is, I think, the most important lesson that we have so far, because many of the world problems could be reduced to graph problems. Say for example, if you're playing checkers and you're creating an AI, what's the least possible movement towards a winning solution? If you're spell checking, what's the least possible what's the least possible strategy to change the letters so that the misspelled letters become correctly spelled letters? You're trading foreign exchange. What's the least possible number of moves so that if I have this money, I put it out in the foreign exchange, and then it comes back to me with some kind of enough with a significant interest. So these are graph problems, and I hope that you will be able to translate what we talked about into those types of applications. Thank you, and I'll see you in the next video. Bye.